Right now, somewhere in the vast darkness of space, a star is being born that will outlive our sun by thousands of times. While our sun will burn out in about 5 billion years, these cosmic marathoners will shine for trillions of years, burning long after every galaxy we see today has faded into darkness. These are the red dwarfs, the smallest true stars in the universe, and they hold the key to understanding the ultimate fate of all stellar life. Today, we're going to explore the incredible story of the longest-lasting stars ever to exist, and why they might be the final beacons of light in an aging universe. The universe is full of stars. When we look up at the night sky, we see thousands of them twinkling above us. But here's something that might surprise you. Almost every star you can see with your naked eye is actually much more massive and much brighter than our sun. The stars that will truly last the longest, the real survivors of the cosmos, are actually invisible to us without a telescope. These are the red dwarf stars, and they make up about 70 to 80% of all stars in the Milky Way galaxy. Yet we can't see a single one of them without optical aid. Red dwarfs are the lightweights of the stellar world. They have masses ranging from about 8% to 50% of our sun's mass. To put that in perspective, the smallest red dwarfs are only slightly larger than the planet Jupiter, yet they're massive enough to sustain nuclear fusion in their cores. This fusion process is what makes them stars rather than failed stars called brown dwarfs. The difference between a red dwarf and a brown dwarf is like the difference between a car engine that just barely starts and one that never quite gets going. That threshold sits at about 75 to 80 Jupiter masses, or roughly 8% of the sun's mass. Now you might wonder, why do these small stars live so much longer than bigger stars? It seems counterintuitive at first. After all, they have less fuel to burn. But here's where stellar physics gets fascinating. The lifetime of a star doesn't depend just on how much fuel it has, but on how quickly it burns that fuel. And massive stars burn through their hydrogen fuel at an absolutely phenomenal rate. A star with 10 times the mass of the sun might only live for 20 million years. A star with 50 times the sun's mass might last just a few million years. These stellar giants are like cosmic sports cars, burning fuel at incredible rates and living fast and dying young. Our sun, which is a medium-sized yellow dwarf star, will live for about 10 billion years in total. It's already about 4.6 billion years old, so it has roughly another 5 billion years to go. But red dwarfs? They're the opposite extreme. They're like cosmic hybrid cars, sipping their fuel so slowly that they can last for trillions of years. The smallest red dwarfs might shine for 10 trillion years, or even longer. To put that in perspective, the universe itself is only about 13.8 billion years old. These stars will outlive the current age of the universe by a factor of almost 1,000. The secret to their longevity lies in their internal structure. Unlike larger stars, red dwarfs are completely convective. What does that mean? Well, in our sun, energy is transported from the core to the surface through two different processes. In the core and inner regions, energy moves through radiation, with photons bouncing around like balls in a pinball machine. In the outer regions, energy is transported through convection, where hot plasma rises and cool plasma sinks, like water boiling in a pot. But red dwarfs are different. In these stars, convection happens throughout the entire star, from the core all the way to the surface. This complete convection is absolutely crucial to their long lifetimes. In larger stars like our sun, only the hydrogen in the core gets converted into helium through fusion. The hydrogen in the outer layers never makes it to the core where fusion occurs, so it never gets used as fuel. It's like having a car where you can only access half the gas in your tank. But in red dwarfs, the convection constantly mixes the stellar material, bringing fresh hydrogen down to the core and carrying helium back up to the outer layers. This means red dwarfs can use almost all of their hydrogen as fuel, not just the hydrogen that starts out in the core. They have access to the entire tank. There's another factor that contributes to their incredible lifespans. Red dwarfs burn their fuel at extremely low temperatures compared to other stars. The core temperature of a red dwarf might be around 3 million degrees Celsius, while the sun's core reaches 15 million degrees. Higher temperatures mean faster fusion reactions, which means faster fuel consumption. Red dwarfs keep their cores cooler, so fusion proceeds at a gentle, sustainable pace. They're not in a hurry. They have all the time in the universe, quite literally. Let's talk about some specific examples. One of the closest stars to Earth is Proxima Centauri, located just over 4 light-years away. Proxima Centauri is a red dwarf with about 12% of the Sun's mass. Scientists estimate it will continue fusing hydrogen in its core for another 4 trillion years. 4 trillion years. When Proxima Centauri finally exhausts its hydrogen fuel, our Sun will have been dead for trillions of years. Earth will be long gone. The Milky Way and Andromeda galaxies will have merged into a single giant elliptical galaxy. Most of the star formation in the universe will have ceased, and Proxima Centauri will still be shining. Another fascinating red dwarf is Barnard's star, the fourth closest star system to Earth at just 6 light-years away. Barnard's star has about 17% of the Sun's mass, and is expected to shine for several trillion years as well. Then there's TRAPPIST-1, which became famous in recent years for hosting 7 Earth-sized planets, 3 of which are in the habitable zone. TRAPPIST-1 is only 9% of the Sun's mass, placing it very close to the minimum mass needed for hydrogen fusion. This tiny star will outlive almost every other star in the galaxy. But what will happen when these long-lived stars finally do run out of fuel? The death of a red dwarf is very different from the death of larger stars. When massive stars die, they go out in spectacular fashion, exploding as supernovae and leaving behind neutron stars or black holes. When medium-sized stars like our Sun die, they swell into red giants, shed their outer layers as planetary nebulae, and leave behind dense stellar remnants called white dwarfs. But red dwarfs? They simply fade away. When a red dwarf exhausts its hydrogen fuel, it will transition into what's called a blue dwarf phase. During this phase, the star will actually get hotter and bluer for a while as it contracts and heats up. This might seem strange, but it's a consequence of the star's changing internal structure. Eventually, the blue dwarf will cool down and become a white dwarf, just like the remnant our Sun will leave behind. But here's the remarkable thing. The universe is not old enough for any red dwarf to have completed its life cycle yet. Not a single red dwarf that formed in the early universe has run out of fuel. They're all still burning, and they'll all still be burning for trillions of years to come. This brings us to an interesting thought. Red dwarfs might be the last stars shining in the universe. As we look billions of years into the future, the universe will change dramatically. Star formation requires gas and dust, and as the universe ages, more and more of this material gets locked up in stars, planets, and stellar remnants. Eventually, in about 100 trillion years, star formation will essentially cease. The universe will enter what cosmologists call the degenerate era, where the only stars still shining will be the longest-lived red dwarfs, slowly working their way through their fuel supplies. After the last red dwarfs finally wink out, perhaps 15 trillion years from now or even later, the universe will enter the black dwarf era. During this unimaginably distant epoch, the cosmos will be populated by the cold, dark remnants of dead stars, slowly radiating away their remaining heat into the void. White dwarfs will cool into black dwarfs. Neutron stars will continue their lonely vigils. Black holes will slowly evaporate through Hawking radiation, though even this process takes an incomprehensible amount of time. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate. That's a 1 followed by 67 zeros. The red dwarfs are also interesting when we think about the possibility of life in the universe. For decades, scientists focused on stars like our Sun when searching for habitable planets. After all, we know life can exist around a Sun-like star because we're here. But in recent years, attention has shifted toward red dwarfs. There are several reasons for this. First, red dwarfs are by far the most common type of star, so there are simply more of them to search. Second, planets around red dwarfs are easier to detect using current techniques. And third, their incredible lifespans mean that life would have trillions of years to evolve on any habitable planets orbiting them. However, there are challenges to life around red dwarfs. These stars are much dimmer than our Sun, so their habitable zones, the regions where liquid water can exist on a planet's surface, are much closer to the star. This proximity means planets in the habitable zone are likely to be tidally locked, with one side perpetually facing the star and the other side in permanent darkness. This could create extreme temperature differences and challenging conditions for life. Additionally, red dwarfs tend to be more active when they're young, producing frequent and powerful flares that could strip away a planet's atmosphere or sterilize its surface with radiation. Despite these challenges, scientists have discovered numerous potentially habitable planets around red dwarfs. The TRAPPIST-1 system, which I mentioned earlier, is one of the most exciting examples. Several of the 7 planets in this system are rocky, Earth-sized worlds located in or near the habitable zone. If life can find a way to exist on these worlds, it would have trillions of years to evolve and develop, far longer than life has had on Earth, or will have before our sun makes Earth uninhabitable. There's another class of long-lived stars worth mentioning, though they don't quite match the red dwarfs for longevity. These are the orange dwarfs, sometimes called K-type stars. Orange dwarfs are slightly more massive than red dwarfs, with masses ranging from about 50% to 80% of the sun's mass. They're not as long-lived as red dwarfs, but they still have lifespans of 15 billion to 45 billion years, much longer than our sun's 10 billion-year lifespan. Some scientists have suggested that orange dwarfs might actually be the best stars for hosting complex life, offering a good balance between lifetime and stellar stability. Let's zoom out and think about what the dominance of red dwarfs means for the structure of our galaxy and the universe. When we look at the night sky, we're seeing a biased sample of stars. The bright, massive stars are visible from great distances, while the dim red dwarfs are invisible unless they're very close to us. If we could somehow see all the stars in the Milky Way regardless of their brightness, the galaxy would look completely different. It would be dominated by dim, reddish points of light. The spectacular blue supergiants and brilliant white stars that dominate our visual impression of the galaxy would be revealed as rare exceptions, cosmic anomalies that live fast and die young. This realization has changed how astronomers think about stellar populations and galactic evolution. When we estimate the total number of stars in a galaxy, we have to account for the fact that most of them are invisible red dwarfs. The Milky Way contains an estimated 200 to 400 billion stars, and the vast majority of them are these long-lived, dim red dwarfs. In fact, some estimates suggest there could be as many as 300 billion red dwarfs in our galaxy alone. Red dwarfs also play a role in our understanding of dark matter and galaxy formation. The mass of all these invisible stars adds up, and for many years, astronomers wondered if red dwarfs and other dim objects could account for some of the missing mass in galaxies. However, careful observations and measurements have shown that even when we account for all the red dwarfs, brown dwarfs, and other dim objects, there's still not nearly enough normal matter to explain the gravitational effects we observe. This missing mass must be dark matter, some form of matter that doesn't interact with light at all. As we develop better telescopes and detection methods, we're learning more about red dwarfs all the time. The James Webb Space Telescope, which launched in late 2021, has the sensitivity to observe red dwarfs in detail and study their planetary systems. Future missions and ground-based telescopes will continue to expand our understanding of these remarkable stars. Every new discovery helps us piece together the complete picture of how stars form, evolve, and die, and how that stellar evolution shapes the galaxies and the universe we observe. There's something profound about the fact that the longest-lasting stars are also the most humble. They're not the brilliant giants that dominate our view of the cosmos. They're not the explosive supernovae that forge heavy elements and light up entire galaxies. They're small, dim, unremarkable red stars that will simply keep burning long after everything else has faded away. They're the tortoises in a universe full of hares, and they'll still be going when all the hares have crossed the finish line and disappeared. In the far future, trillions of years from now, any civilizations that exist will likely orbit red dwarf stars. These will be the last bastions of warmth and light in an increasingly cold and dark universe. The night sky from a planet orbiting a red dwarf in that distant era will be almost completely black. No galaxies will be visible. No nebulae will glow in the darkness. The cosmic microwave background will have cooled to nearly absolute zero. But there will still be that one red sun, small and dim, providing just enough light and warmth for life to continue. And then finally, perhaps 15 or 20 trillion years from now, the last red dwarf will exhaust its fuel. The star will shine steadily for a few billion years more as it transitions through its blue dwarf phase, then gradually cool and fade. The last stellar sunset will occur. The last photon from the last star will fly out into the void. And the universe will enter the long darkness, the age of stellar remnants and black holes, a darkness that will last far longer than the age of stars ever did. But even that darkness will eventually end. In the almost unimaginable future, perhaps 10 to the 100 years from now, even the black holes will have evaporated. The universe will be filled with nothing but scattered particles and radiation, all at the same temperature, with no possibility of any organized structures or processes. This is the heat death of the universe, the final equilibrium state predicted by thermodynamics. It's the ultimate fate that awaits all things, an end not with a bang but with an eternal, unchanging whimper. Yet standing between now and that distant end are the red dwarfs, the longest-lasting stars in the universe. They represent the cosmos at its most efficient and its most enduring. They're a reminder that in nature, it's not always the biggest or the brightest that lasts the longest. Sometimes it's the small and steady that endure. These humble red stars will keep vigil over the aging universe, burning patiently through trillions of years, the last lights before the coming of the eternal night.